let's dive into some of the content for what's new in SolidWorks Flow Simulation and Plastics 2016. We're going to start with flow simulation here. And one of the big changes for flow simulation in this release of SolidWorks are some changes to the mesh, the way that the mesh is set up in the property manager, and some new options that will hopefully make your day a lot easier when it comes time to generate that mesh on the new solid model. So let me jump in here and I'll try to show you first of all what this new mesh interface looks like and some of these options that I'm referring to here. So we're going to open up SolidWorks 2016 here, the newest release, and on my screen what I've got is a model that we've been working on here at Hawkridge Systems. This is the HRS 9000 Hawkeye drone. So it's an actual little remote quadcopter drone that we're trying to design here at Hawkridge. And so one of the things that we wanted to test out were just the basic aerodynamics of the frame and, of course, the plastic body, the fuselage that you see there. So I decided to set up a flow simulation study on this, and some of these new meshing enhancements have made it a little bit easier to get through some of that setup work and to run an analysis more quickly. So first of all, what I'm going to do here is switch to another configuration that I have of this assembly that we've made, which is very simplified, really just focuses on the body and the shell itself without any of the internal components. And that'll make, first of all, simulating it a lot faster, but it'll also keep things simplified where maybe we could even run an aerodynamics test like this before we've even built out the rest of the geometry. So I'm going to turn on my flow simulation here and check out the study that I've got set up. And so there are a couple things that I can do here with the meshing to speed some of the analysis up. So first of all, if you take a look here, if I want to go modify the mesh, the button to do that is still in the same place in the flow simulation tab on the command manager here. Once I've turned the add-in on, there's still the global mesh button here, which is a little yellow box, looks like a kind of a block of mesh elements or mesh cells. But you can also go down here to where it says mesh in the setup for the project under input data, and you can right-click on where it says global mesh and go to edit definition. And you can see now that the mesh menu has significantly changed. There's a whole new layout to it. We think hopefully it's a little easier to understand than all the different tabs that used to be there if you tried to do the manual mode before. And it keeps everything in kind of one place. So first of all, we always have had the automatic mesh setting. As you may remember, we could pick a slider level from 1 through 7. 1 through 8 was what it used to be, but we've actually changed it to 1 through 7 now. And so there are a couple basic options here that we've added. First of all, you can show the basic mesh right on the computational domain and on your model before you even create anything. And for those of you that aren't familiar, the basic mesh is sort of the starting grid that gets created before the mesher goes in and tries to refine anything to capture the actual geometry of your model. So this is like the starting grid. So you can see that very quickly with one button click here. And some of you might notice that the cells are not actually the same size or shape everywhere in the analysis. That's always been true in flow simulation, but it wasn't particularly apparent. Not everyone was aware of that. And typically that's intentional because it gives you more detail with smaller cells down where your model is and bigger cells as you get further away. They sort of stretch in that direction. But if there are cases where you don't want those cells to just automatically adjust or stretch their size like this, which again the mesher has always done by default, you can override that if you like, and there's a new checkbox called uniform mesh, which will ensure that every cell is the same exact size of the starting grid. Now again, this does not include any refinements that might happen where the cells start to get split up to match the real geometry, which is the next step of the mesh. This is just talking about the starting grid, so to speak. So this optional uniform mesh can definitely basically ensure that you don't have a change in accuracy depending on which part of the computational domain you're in, if you want to ensure that you have the same level of detail everywhere. There's another option here called close thin slots. This is something that really has been kind of a needed feature in flow simulation for a long time for certain models. And that's because, as you might be aware, a lot of models, the way you build them in SolidWorks, are not necessarily airtight. If you're making an enclosure for electronics box, let's say, you probably don't have every last gap in that sheet metal enclosure filled in. Or even if it's supposed to be once you actually manufacture it, maybe it gets welded together, you may not have modeled it that way in SolidWorks. And so in flow simulation, you either had to just accept that those gaps would be there in your analysis and maybe do an external study on it, or you would have had to go in and manually model features in to close up those gaps. Well, luckily, in 2016, we have this new feature, again, in the same mesh property manager. If I go right here to the same global mesh settings, and it's called close thin slots. Close thin slots. So what does that do? Well, before I show you the effect of it, let me show you another version of this study up here where I didn't use the closed thin slots. And I'm just going to briefly show you the mesh on this model. And you can see that, again, there's some refinement that's happened now in the mesh. And I've got some small slots and gaps and other things in the frame, the body of the quadcopter. And you can see that there are some mesh elements or mesh cells inside those slots, although they're not refined particularly well. And so that's what the mesher would have done in 2015 or earlier releases. But in this particular case, you probably can imagine that the real analysis would not allow airflow to have any kind of passage through these slots because there would be fasteners and other components filled in there. So if I want a quick way to ignore all those little slots and not have to worry about meshing them well to get a realistic result, I can immediately check the close thin slots option and it'll turn off all of those cells. So here I can switch to this other version of my analysis here. This is another project which I cloned. And by going into the mesh settings here and simply checking that box, the close thin slots box, I type in the height of the slot that I want to close off, and it'll automatically go in, and when it generates the mesh, it will detect the size of those slots, and it will basically fill in the slot by turning off that cell in the mesh. So once I was to generate the mesh on this particular version, the study, if I went back to the same exact plot that I had before, we can see here that I've changed the background color mesh plot just to make it easier to see. And if I zoom in and look at these slots, you can see that they're no longer included in the mesh. There are no cells inside the slots. You can see there's no grid lines there, and it's not colored in. So those would be treated as part of the body here of the frame. So again, that's a perfect way to easily get rid of any small gaps without having to change anything about the geometry. So closed thin slots will hopefully be a big time saver in the future. Another enhancement to the meshing is something that we call equidistant meshing. And this is a particularly useful problem, or excuse me, useful capability for some aerodynamics analysis or other external problems. In the past, in flow simulation, if you had an object where you wanted to do an analysis of airflow around it, you obviously knew you had to have pretty good mesh at the surfaces of the body. And so, for example, if we look at this same study that I'm looking at right now, even with the closed thin slots option enabled, if I was just to look at the mesh on this analysis, maybe on the side plane or something like this, I can see that, again, the mesh right at the surface of the front shell, for example, is pretty good. But as you get away from the front shell, the mesh coarsens up very rapidly. And in the past, the only way to really get better refinements in those areas, which can be really important, the upstream and downstream of your craft, was to either refine the mesh everywhere, or you'd have to use some pretty advanced options like the solution adaptive meshing, which would automatically detect where you have discrepancies in things like the pressure or velocity results, and it would fill them in with more detail. But again, the solution adaptive is a pretty advanced option, which required a lot of knowledge about the mesh to get to work properly. And so this new option called equidistant meshing makes it easy to instead just pick some faces on your model and select that you want the mesh to just be refined in a number of zones, sort of a certain distance away from those faces. So if I switch to another version of the project called Equidistant Meshing here, what I've now got is an extra mesh control called local mesh 2 in this case. And this is very similar to what we used to call the local initial mesh, except it's just in a different spot in the tree here with a different name. And this is where we would apply any other mesh settings we want to specific parts of the model. So for example, here I could refine the mesh around any particular component. I could refine the mesh inside the gaps of a certain part. But what I'm doing in this case is using the new equidistant refinement option, and I'm clicking the faces of the front body shell and the side here, and checking this equidistant refinement option. And now what it allows me to do is pick a number of shells, which is kind of like the number of zones that I want to have extra refinement in them. And then I set the maximum equidistant level. So basically, how many levels of refinement do I want from the size of the cell that would have been there without any extra equidistant refinement. And then these two boxes set what the distances are for these zones. So I've said the first zone would be out to 0.25 feet, so quarter of a foot, so 3 inches. And then there's another zone at 0.5 feet, or 6. And when I generate the mesh, you will see that there are basically these two regions of extra refinement in a similar shape to the faces that I've picked here with that extra level. And it will always be one level of refinement difference between each of these zones. So when I go to generate this mesh, you can load in the results here. And let's look at that mesh cut plot again this time, just with the mesh, no velocity or anything. And here you see the effect of those zones that I've created. So out here in the front, you can see that the cells are pretty much the same size they would have been if I hadn't used this option. But now I've got these two refinement going down 1 and then 2 levels, basically, from the mesh that would have been at the face of the object. And so now that extra refinement is contained only to right in the front of the craft, which, if you're kind of into aerodynamics problems, you know can be real important. And when we go look at some results afterwards, I'll show you some of the differences in what this extra refinement can make in the results and how much impact it has. So those are the key changes related to meshing. Again, new interface, and we hope new options that'll give you more power than you had before at refining mesh in areas you want, not having unnecessary detail anywhere else, and generating the mesh more quickly without having to modify the model in advance. Now, we've also got some new solver improvements in Flow Simulation 2016. The main one is that we have a new, what we call nested iterations transient solver. So this transient solver basically is meant to solve one problem, which is that if you were trying to run any kind of time-dependent or transient solver in Flow Simulation 2015 or earlier, the time step that was needed to get good airflow results and make sure that the air patterns and currents are developed right was really small. And that meant that if you had, let's say, a problem of a box heating up with some components in it, or really any kind of thermal cycling or other effects, the length of time for the analysis might be 6 hours. You know, you want to simulate something running all day or sitting out in the sun all day. And so the solve time would be very high because, again, the time step would need to be small to see what the air currents are doing. What this nested iteration solver does is it basically uses a smaller time step to solve certain parts of the problem, like the airflow patterns, the air currents, but uses a larger time step for other things like the heat transfer aspects. And so the effect of this is that when you're running a simulation, you can now just set the time step manually at a larger value and basically do that safely without having to worry that you're distorting the results in any of the airflow or liquid flow properties. So the nested iterations will basically automatically update the airflow currents and other important parameters even though you've specified a much larger time step, more related to just how often you want to see the thermal properties of whatever you're simulating. Maybe that's just how frequently you need to see the temperature of a chip. So you can put 10 seconds in for the time step size if that's all you really care about for seeing those results. And the nested iterations will ensure that there's still a high level of accuracy. And you can see that some benchmarks have been done and solve time has been drastically reduced in certain cases. On average, it's probably more like 50%, but it varies from simulation to simulation. Another solver enhancement here is if you've ever looked into setting up the light sources and things in an assembly in SolidWorks, we have something that was added in SolidWorks 2014 called the Solar Access Study. And the Solar Access Study was basically meant to simulate a moving light source like the sun to see what the shadows on your model would look like for things like solar panel placement or just general illumination concerns. So that Solar Access Study was only really for creating animations before, but the nice thing about it had sort of a database built in where it could predict where the sun would be at any given time or day. In flow simulation, we've also had a database where you could pick a day of the year and a time and a city from the engineering database, and it would show you approximately where the sun should be based on that information. But what they've added now in SolidWorks 2016 is that if you want to do, again, a transient simulation, something that's time dependent, and if it's, let's say, 6 hours or 8 hours, or you're trying to simulate most of the day, the sun obviously would be moving during that time. And it wasn't always as easy to simulate that in flow simulation, to simulate a moving source of thermal radiation. Well, now if you've done this solar access study on your assembly, you can select the new model sunlight option under the solar radiation menu in the wizard, and that will automatically import all of those same radiation parameters from the solar access study. So again, as long as your length of time for the simulation is set right to whatever number of hours it is, the sun will be in the correct position based on that solar access study throughout the whole simulation. Okay, let's wrap up and look at a couple enhancements to results viewing with flow simulation. The main one is that we have some new mesh refinement plots and also something called symmetric results. So with the mesh refinement plots, of course, we've always been able to view the mesh in SolidWorks flow simulation. Again, I've just shown it to you here in these couple different examples. But what we've added now in 2016 are some new ways to view the mesh and some new parameters as well related to mesh quality. So first of all here, if I hide this plot, I can right-click on Mesh and click Insert. And this gives me some different options where I can either select faces of the model, or I can also just use the Use All Faces option here. And basically, by getting a preview, I can project things like the refinement level or the curvature and tolerance criteria onto the model itself. And I can also use a section plane, like the right plane, for example, to see what that looks like on a cut plot. So for example, the refinement level here is literally just showing me how many levels the cells have been split down to from that initial grid, from that basic mesh grid that we started with. So for example, the blue ones here, if you look at the chart, are level 0. The light blue is level 1 because it was subdivided one time. Green is 2, and so on and so forth. So again, it makes it much easier to tell exactly what cell size I'm talking about when I look at all the different areas of the model. And again, these other ones like curvature and tolerance criteria can help you predict why the mesh was refined in a certain area based on the geometry. Okay. Also, we can plot what's called the aspect ratio in certain cases as well. And also, if we create a cut plot, there are some new geometry parameters which are available in the expanded menu. If you want to display your contours here, we can add new parameters under geometry, things like the brick quality. And brick quality is basically a plot showing how well the cell itself was sort of cut or subdivided out. And if I just turn on the preview here, for example, level 0 is good, which means that the cell itself was properly trimmed, and the boundary here of the partial cell itself is representative of the original geometry. And you can see on this plot that it shows you the actual boundary sort of overlaid onto what the original model looked like. So you can tell how closely the cell itself is approximating that curvature. And if there were any cells that for whatever reason didn't get trimmed properly, those would show up in other colors. So again, that's related to making sure you have a good mesh, more on the results side. Probably the more exciting feature that we've added related to results viewing is what we call symmetric results. And so, of course, in any simulation, if you have a model that's symmetric, like this small quadcopter, we've probably known for a long time that you could split that simulation in half and basically run the analysis on only the left or right side of the model, assuming all the conditions were also symmetric, because that would obviously save time to set the analysis up that way. For example, here I'm using the symmetry option where I've set up the computational domain of this problem to only be on the left side of the quadcopter, and the dashed box representing the other half of the problem is really just a virtual computational domain where all the results are the same as what would be on the left side. So I've always been able to do that to speed up my simulation, but if I were to run the problem this way, I could only see the results on the half of the model that I ran the simulation on. I wouldn't be able to make it look like I had included the entire model. Well, now I can. If I look, for example, at a streamlines plot here, there's a new mirror results checkbox that's been enabled, and as soon as I show this plot, you can see that even though I only ran the simulation on the left half of the quadcopter, I can view the results on both sides of it, where it's simply mirrored over. And this is great if you're trying to show some simulation results to maybe a manager or someone at another company that's not familiar with the way simulation works, and maybe needs more clarity on what this looks like in the real world. So again, that's available for cut plots like that, and also surface plots as well for things like pressure distributions. All right, let's switch gears here to plastics as we wrap up. Plastics has fewer enhancements this year than flow simulation, but there is something that's really important that we want to point out that has been added, and that's a new solver. It's called the 6SAM solver, which is a technique that has been used successfully in other simulation tools in the past. And just to give you a bit of background, prior to 2016, in previous versions of SolidWorks Plastics, again, the injection molding simulation tool we have, there previously were two solvers that were available. One was called direct, and one was called indirect. Indirect was the default solver, whereas direct was another solver you could switch to if you wanted specifically to increase the accuracy of certain results. Either solver would give you the same general flow patterns. It would allow you to predict weld lines and sink marks and things like that. But if you specifically were trying to look at what the flow front of the plastic would look like, which is typically necessary for certain problems like jetting, the direct solver was more accurate. But it took a lot longer to solve as well in that case. So the purpose of the new SAM solver is to allow you to get sort of a combination of both. It has the accuracy of the direct solver for all results, jetting and other things included, but it's faster than the direct solver, more comparable to what we used to call the indirect solver. So if I open up this front body shell of the drone, where I just wanted to simulate filling this part with the molten plastic when I manufacture it, I can look here first of all at, for example, the indirect solver, the old one. And we can see that, of course, if I go into the solver menu here, if I look at the setup under SolidWorks Plastics, there's that new option in the drop-down, which you'll see called 6SAM solver. And the most important thing to know about this new solver selection when you get into this menu is that it's actually now the default. So if I open up my fill settings for this model, and I go under solver settings here, and go to the options, it's listed right here under the volume of fluid algorithm. And I have 6SAM selected here, and in 2016 and any subsequent versions, if you create a new analysis, it will have the 6SAM solver selected as the default. Previously, indirect was the default. So your simulations may take a little bit longer compared to what you would have expected in the past, but they will have the necessary accuracy to get any result, including flow front shape and topology. So for example here, if I bring up a flow results plot, this is what was generated using that new 6SAM solver. You'll see when I animate this, not only are the final results, like the fill time and pressure, accurate, but if I were to show what we call this ISO surface mode as we animate it, the actual shape of the flow front itself has more detail. And if we do a little benchmark here, which we've done in the past, to compare the three solvers on the same simulation, they have the same exact mesh, same number of elements, but the CPU time for the 6SAM solver was much closer to what it used to take to solve it with the indirect method. So we get the accuracy of the direct solver without what used to be about a long computation time. So that's something exciting that really doesn't require you to change the setup in any way. It's just a benefit that you'll realize when that solver is selected by default for any new analyses. Another enhancement to SolidWorks Plastics is if you ever want to do a warpage calculation in the past, which warpage is meant to predict sort of the deformed shape of part after it comes out of the mold and has deformed in some way. Previously, if you were going to do that kind of calculation, it would run a stress analysis based on the temperature changes and the in-mold stresses and things. But the mesh itself would only use what we call first-order elements. Now, in 2016, that mesh will use what we call high-quality or second-order elements, which is the same kind of element that we use in SolidWorks simulation by default, which has much better accuracy for stresses. And also deformations, displacements. So now that will be much more realistic, and the results should correlate better with what you would get if you were doing a normal stress analysis in the SolidWorks simulation. Finally, for plastics, just on sort of the user interface and report generation side, you may notice that we've continued to refine the user interface and update it along with all the rest of the add-ins for SolidWorks. So there's more consistency, of course. And specifically in the report generation, if we go and generate that report in 2016 now, you'll see a much more professional looking report. It looks more consistent, again, with all of the other products that you may see, like the simulation or flow simulation reports. So we can generate a report in Microsoft Word or PowerPoint, or both, which we've always been able to do, but the format is much more consistent now, just like you'd expect. Of course, the wizard comes up and allows you to select which images and things you may want to include from your results. Of course, you can give it a title, and you can also pick from a number of templates. For example, we have this classic template, and we also have a new light template, which is basically a briefer report, but still has been improved for 2016. So that about wraps up the enhancements to SolidWorks Flow Simulation and SolidWorks Plastics, two of our most advanced simulation tools, part of the SolidWorks family for 2016. If you have any more questions or if you'd like more information on what's changed or what's coming, maybe new examples that we put out to showcase some of these feasibilities, just pay attention to, of course, our blog and content on the website. We're trying to update that, and as always, you can send us email and give us a phone call up the support line, and of course, the technical support team has dedicated simulation experts that are familiar with these enhancements and will be able to guide you through how they're being used in 2016. Just to recap before we finish here what some of the upcoming webinars are going to be on, let's look at the schedule for the next couple weeks here. Today, of course, we are wrapping up just now with this product education session on what's new in flow and plastics. Next week for Thanksgiving, we're actually taking a week off for the holiday break, so There won't be any webinars on November 25th, but following that, we'll pick right back up again, starting off our December webinars for 2015 to close out the year. We'll be doing a SolidWorks product demo entitled Design for Cost with SolidWorks Professional using plastics. That's going to showcase how the costing tool specifically can be used for plastic part design cost. And then also a product education at 11 a.m. Continuing our What's New theme. It's going to be What's New in CamWorks 2016. Again, CamWorks is the gold partner built-in CAM software for SolidWorks that Hawker Systems also offers. So with that, if we have any questions that anyone has, we'll try to make sure we've gotten to answering all of these before we end the webinar here. Just to recap some of the questions we had, looks like there were some audio issues, so I apologize for that. Not sure what the issue was with some of the bandwidth that we were looking at there, but hopefully it wasn't terrible the whole webinar. Hopefully it was corrected. But again, if you have any questions about the meshing enhancements, the new result viewing, anything like that, go ahead and pop them into the list here, into the questions panel in the GoToWebinar interface. Sylvia and I will try to get to that. Otherwise, if you don't have any more questions for now, of course, you can email us. My personal email is on the screen there, or you can always contact your account manager or the tech support team. Again, the tech support website is listed on the screen there, where you can go for phone call information or to start a new ticket, of course. Anyway, if no one else has any other questions, again, thanks for attending today. Hopefully you're all going to be enjoying SolidWorks 2016 soon, and we'll see you next time.